I think quantum mechanics has opened a lot of scientists to the profundity of nature.
The theory makes strange predictions about the nature of reality and the role between the observer and the observed.
What role is it that humans really play in deciding just where the atom is?
I couldn't quite see how the determinism of the atoms in my brain and my subjective impression of free will could be put together.
We need to rethink metaphysics and ethics and so on in light of quantum mechanics.
In a sense, all of life is unpredictable.
Is life unpredictable? Do we choose our thoughts or our path through this life? Are we beings who truly have free will to decide which path we're going to take or which choice we'll make? Or do we live and breathe in a completely deterministic world? Are we merely an aggregation of particles that react and respond in predictable ways? Welcome to Matter and Beyond. I'm your host, Mary Lynn Chiave. In this program, we're going to explore quantum theory and what it might be able to tell us about ourselves and how we interact with the people and the world around us. If we live in a world where the behavior of particles cannot be predicted, then can we conclude from this that human beings and the human mind are just as unpredictable as quantum particles? We met with Nobel Prize winner Dr. Charles Townes in Berkeley, California. Townes is the inventor of the maser, which led to the laser, which has changed our world in profound ways. Although it is a fundamental branch of modern physics, quantum mechanics is puzzling in many ways. The foundation of quantum mechanics contains certain counterintuitive elements. One of them is called particle-wave duality. Quantum theory asserts that everything, whether it is matter or light, can be considered as both a wave and a particle.
Well, quantum mechanics describes how atoms and molecules behave and so on, and that's a very important part of us.
Many developments in science and technology have only pragmatic results. Progress in superconductivity, plasma physics, and microbiology have all resulted in various applications through technology. But very few scientific theories have altered the way we understand the world and ourselves.
It really changed our views of what the physics is like and what the world is like a great deal. Changed very fundamentally and philosophically.
When the motion of atomic particles at the quantum level are compared to the motion of macro-scale objects, there is a dramatic difference. The principles of classical mechanics explain the motions of everyday objects, such as a falling apple or a projectile motion of a baseball.
No, if we throw a baseball this way, we think we know exactly, once we see it start going, we think we know where it will go. And now, if we throw an atom, then quantum mechanics says that's not predictable. It says the baseball even isn't completely predictable, but it's almost precisely predictable.
If the initial conditions are known, one can calculate the motion of a baseball with great accuracy.
So it's predictable with precision, any precision we can measure. But for an atom, much smaller mass, it's not predictable. It may go this way, up, down, left, right. It is not predictable.
Unpredictability at the atomic level is the result of Heisenberg's uncertainty principle. Its most mysterious aspect is related to the fact that objects have different properties, such as position, speed, mass, lifetime, and spin. When a certain aspect of a property is measured and found, its uncertainty disappears. But then other properties may become uncertain.
But it's very puzzling also, because it says that something, you send a small particle along through a hole, let's say, it may go this way and that way, and one can never know which way it goes. And you don't know until you look at it, and there it is. But before you look at it, it may be here and may be there and may continue to be there. But once you look at it, then it's definitely there, you see.
The laws of quantum physics tell us that when we throw an atom, not only can it go many different ways, it can be in all of those places at the same time, according to some interpretations of quantum mechanics. And we never know for sure until it's actually measured.
If we detect the atom off here, then we know, okay, it's going this way, and that's it. But until that time, where the atom is maybe in all these different places at the same time, or at least in any one of them, and we don't know.
According to quantum theory, there's a special role that the observer plays in determining the outcome of a specific process. But why should this be? It's an important question to ponder. Could it mean that in fact everything in the universe is actually connected rather than separate and distinct, as our modern view would lead us to believe? Nobel Prize winner Charles Townes struggles with this question as well.
Now, why do the observations of humans have such an important effect on this? And that's a little bit puzzling. What role is it that humans really play in deciding just where the atom is?
For Townes, uncertainty and unpredictability on a smaller scale could have far-reaching consequences, since everything is built from atoms and molecules.
It also means that, in a sense, all of life is unpredictable. We are made of atoms, and these atoms do things. So we can sort of guess roughly what's going to happen in life, but we don't know for sure.
In a series of lectures at MIT in 1964 called the Messenger Lectures, Richard M. Feynman said, "I can safely say that nobody understands quantum mechanics, so do not take the lecture too seriously, feeling that you really have to understand in terms of some model what I am going to describe."
In any case, quantum mechanics is a really remarkable and strange phenomenon, and we don't understand it all. And what it also says that things are not predictable. It has changed our ideas of deterministic world. This is not a deterministic world. Not only is it not deterministic, but you can never predict what it's going to do exactly.
What does the unpredictable nature of matter on the quantum level reveal to us? In a completely deterministic, mechanistic universe, there shouldn't be any place for free will. Newton's 3 laws of motion state that matter is subject to laws of its motion. If one knows the initial position, initial velocity, and the forces acting on it, one can determine the motion precisely. This led some philosophers to conclude that free will is an illusion. According to Dr. Robert John Russell, seeking a middle ground perspective on free will versus determinism would be more productive.
One extreme is the one in which you think the world is fully deterministic, the Laplacian world that we got from Newton. And if that's the case, then it's pretty clear free will isn't possible, because how could I decide to raise my hand if physics determines what I do and physics is lockstep determinism?
Some philosophers, like the 18th century German philosopher Immanuel Kant, realized that it was necessary to establish the ideal of free will upon a moral foundation.
Because he realized that in the Newtonian framework, free will doesn't make sense, so it must be grounded someplace else. And he said, well, it's part of the moral sphere. It wouldn't make sense to think of yourself as a moral agent if you didn't have free will, right? So he needed that as a priori assumption for his moral ethics.
In his book, Critique of Pure Reason, Kant said, quote, "All the preparations of reason, therefore, in what may be called pure philosophy, are in reality directed to those three problems only: God, the soul, and freedom," unquote. And this reasoning leads Kant to a critical question. He says, quote, "What ought to be done? If the will is free, if there is a God, and if there is a future world," unquote. And so according to Kant, the concept of free will cannot be grounded in scientific inquiry, but must be solely grounded in a moral foundation.
Interestingly, science has changed, and even as Kant based his metaphysics on Newton's science, we need to rethink metaphysics and ethics and so on in light of quantum mechanics.
Discoveries in quantum mechanics have reignited and influenced the discussion about determinism versus free will with regard to the human spirit. Now the question is, can we understand more about the concept of free will by understanding more about uncertainty in quantum mechanics?
Not reduce it to quantum mechanics, just see what openings quantum mechanics provides that Newton's mechanics didn't provide. So that's one. Now we're on the scholarly side. Does quantum mechanics provide some of the necessary things you need to talk about free will? Is that true? I think it does provide some of those, but very small parts of it.
Russell believes that we should be careful not to make far-reaching assumptions based on quantum theory. He gives as an example the movie What the Bleep.
The other extreme is the craziness of a movie like What the Bleep, where, yes, it is true that if you do an experiment, in some ways you influence the experiment, but you can't measure the spin of an electron and make it into a zebra.
So which perspective constitutes a middle ground? Quantum mechanics destroyed the notion of determinism, but what does it really offer as a substitute for a metaphysical worldview?
It is true that as you experiment with nature, as you perform experiments, you can't reduce to zero your influence on the things you're measuring. Classically, you could. That was the ideal of classical physics. You could in principle, measure existing properties without perturbing them.
In quantum theory, any effort to measure an object must involve a particle being sent to the object, whether it is an electron or a photon, thus forcing the particle to interact with the object.
So in essence, you disturb it by measuring it. That was Bohr's idea of measurement. In that sense, you're interacting with the thing. You're trying not to interact with it, but just purely measure. But there's a more profound sense in which the thing is sort of interacting with itself. That is, there is an implicit, non-local, non-separable nature to quantum phenomena, which even aside from measurement, it opens the world to radical novelties that one doesn't have control over.
Dr. Paul Davies is director of Beyond at Arizona State University, a pioneering center devoted to tackling fundamental questions of science and philosophy. One area of research focuses on the foundations of quantum mechanics and the nature of reality. Davies has been fascinated by the mysteries of nature since he was a young boy. He longed to know how the universe worked.
And from the earliest age I can remember, I was fascinated by the mysteries of nature. We're surrounded by this wonderful universe, and I wanted to know, how does it all work? What's going on? And so probably from the age of about 12, I had in mind something like being a theoretical physicist. I didn't really understand what physics was in those days, but looking back, I'd already for several years been fascinated by things like atoms and stars and how all these things worked and were put together. And so certainly by my mid-teens, I absolutely knew that this was what I wanted to do as a career.
Davies was drawn to the big questions, the questions that human beings have wrestled with for centuries.
So during my career, I've always been drawn back to these very deep issues of existence, not just free will and consciousness, but the nature of time, the origin of things, how did the universe come to exist, how did life come to exist, and human destiny. What are we all doing here and where are we going? And if we think a million or a billion years hence, what will the universe be like and what will our descendants, if any, be like? So I've always been fascinated by these big questions, the big questions of existence. And I found that having a thoroughly strong background in theoretical physics is easily the best way of confronting them.
His interest in studying free will was triggered by a personal experience.
But curiously, around about the age of 16, I was seized by a sort of existential crisis. On the one hand, I understood that our brains were made of atoms, and atoms have to do what atoms have got to do. On the other hand, I have a sense of free will, of being free to choose between alternatives, and I couldn't quite see how the determinism of the atoms in my brain and my subjective impression of free will could be put together, and that caused me a real headache, and I thought I want to get to the bottom of all this.
According to Davies, many of his students have been attracted to quantum physics because they think it will help them understand the nature of reality.
I think a lot of people who dabble around in quantum physics just have a sort of mystical view, and they never actually solve Schrodinger's equation, for example.
Although quantum mechanics is tremendously appealing because of its mysterious nature, most of the work currently done has to do with its practical applications. The theoretical or computational work behind it involves somewhat mundane mathematical work.
It consists of solving Schrodinger's equation in various potentials and making contact with atomic physics and the experiments and so on.
While quantum mechanics has challenged and changed our perception of the nature of reality in many ways, how it relates to fundamental questions of existence is still up to debate, according to Davies.
Yet it is certainly true that the theory makes strange predictions about the nature of reality and the role between the observer and the observed, and that the physics community at this time has no real consensus about how to deal with that.
While we may be eager to find meaning in this new understanding of physics that relates to our lives and the way we think, Davies points out that we have to be careful not to take a quantum leap to conclusions.
Now there is a tendency, and you have to be really careful, of saying, well, so quantum physics has a mystery at its heart, consciousness is mysterious, so maybe one mystery explains the other. Doesn't necessarily follow.
So back to our central question. Can the behavior of matter at the quantum level help us to understand the function of our brains and therefore our thinking processes? And if atomic and subatomic particles appear to behave in an unpredictable fashion, can we assume that since our brains are made of atomic particles, that they too behave in an unpredictable fashion? Davies doesn't believe that this is a wise leap, because the human brain consists of a completely different environment that is not conducive to quantum particles.
It's just that in practice, for significant quantum effects to manifest themselves, you need to be in a very controlled environment, preferably at an exceedingly low temperature, and to screen out all of the noisy influences from the surrounding world. And it seems to me the brain is anything but that sort of system.
Davies explained that quantum effects on a large scale manifest only at very, very low temperatures near absolute zero.
This is a hot, wet, noisy system, and it's really hard to see how quantum mechanics could play a role over anything other than a scale of a tiny fraction of a cell. We can imagine down at the level of molecular motors and things inside cells that quantum mechanics may be important, but on a multicellular scale, it seems almost impossible to imagine that it would play a significant effect.
In order to observe quantum effects in action, one needs to take into account the wave nature of quantum systems, and these waves are very delicate. He explains only if we overlap these waves in an organized way, we may begin to see patterns.
But once you start scrambling waves up, you just imagine throwing a whole lot of sand into a swimming pool, and you get all these ripples and they all interact and you have a mess. You don't have nice little cooperative waves. And that's the problem with the waves in the brain, because they're going to be jiggled around by heat, in effect.
In the presence of heat, atoms, molecules, and tissues begin to vibrate, which in turn makes the interactions between the waves very chaotic, explains Davies. All the relationships between the different waves are scrambled up.
And that makes it very hard to see how quantum effects could exert any sort of serious importance in the brain. Now, I may be wrong. It may be that there are mechanisms which can survive even at high temperatures, and people have looked at that, but so far there's no evidence for that.
Although quantum mechanics opens up new discussions on free will, according to Dr. Towns, the mystery of free will is not necessarily solved by quantum theory.
We have a theory that's been developed showing we can test whether or not there can be any outside force of any kind coming in to affect quantum mechanics. And we do experiments to show no, there can't be. There can't be any outside force, nothing new, nothing that can affect quantum mechanics. So that doesn't give us free will in accordance with our present understanding of science.
While some scholars and scientists believe that because of the uncertainty principle and because certain types of matter appear to be unpredictable, that we can conclude from this that human beings have freedom of choice or free will.
Things are not predictable, but that doesn't mean we have any control. That doesn't give us free will or anything. And quantum mechanics is very, very puzzling. And probably we don't understand it very fully yet.
Although determinism, or a mechanistic view of the universe, doesn't really allow for the concept of free will, Dr. Towns emphasizes that unpredictability is not equal to free will. On the other hand, if we do indeed have free will, then, according to Towns, maybe there is something we're missing.
How can we have free will when science doesn't allow free will? Well, that says there must be some new laws, something new there. Maybe there's a completely new dimension somehow. A spiritual dimension or some new dimension or something. Something is going on there if we really believe we have free will. Maybe we don't. Maybe we don't have free will. But if we really believe we have free will, there has to be something completely new there.
According to Russell, the results of experiments in quantum mechanics have perplexed and invited many scientists and scholars to consider the nature of our world in a radically different way.
I think quantum mechanics has opened a lot of scientists to the profundity of nature and to the kind of limits and veil through which we see nature and describe it. But again, that's also because we know so much about nature with quantum mechanics we didn't know. So we've both learned to prevent us a lot more. And what we've learned is how really supple and subtle nature is.
As we've heard from Dr. Towns, Dr. Russell, and Dr. Davies, the principles of quantum mechanics have shaken the foundation of the traditional view of the world of matter on the subatomic level. But how far up into the macro world will we feel the vibration? Perhaps the answers are right in front of us or all around us, and we just don't have the apparatus or the instruments or the perception to pick up the signal. Thanks for taking this quantum leap with us and watching Matter and Beyond. We'll see you in the future.